Find f of g of x in the domain of the composite function. Okay, so this one's asking us to do f of g of x. So f is the outside function, it's the first function. We're going to copy it down, and every place that it has an x currently, we're going to leave a space. So we're simply going to say space squared plus 3 times space. And in the space, we're going to put in the g function. So the g function here is 2x squared minus 1, and 2x squared minus 1 goes there as well. Now from there, we just do the work that's implied by the expression. So we have 2x squared minus 1 squared. So we have to write that down twice and multiply, right? Plus 3 times, we can actually work this one out as we go, right? 3 times 2x squared minus 3 times 1, right? Or minus 1 times 3, however you want to look at that. Okay, either way, let's go ahead and do the foiling then. So this guy times this guy is going to give you 4x to the 4th. And then 2x squared times negative 1 gives you negative 2x squared. And then negative 1 times 2x squared gives you another negative 2x squared. And then negative 1 times negative 1 gives you positive 1. Then the 3 times the 2x squared there gives you a positive 6x squared. And then negative 1 times 3 is negative 3. Okay, combine like terms. All the x squareds that can go together will go together. Looks like the 4x to the 4th is by itself. But the negative 2x squared will make negative 4x squared. If you combine that with a positive 6x squared, you end up with a positive 2x squared as the net result of that, right? And then finally, you have 1 minus 3, which is going to give you negative 2. So there's your function. This is your f of g of x function, right? That's the composite function. They want us to state the domain. Now, to state the domain, you want to consider what I like to call the final function. And what I mean by that is that you need to look at the final result, which is this f of g of x function we have in front of us. And for that, we can tell what? The domain is from negative infinity to positive infinity. If you're wondering why that's the case, it's because that's a polynomial function, and we learned earlier that polynomial functions have a domain that's equal to all real numbers, right? Now, there's just no place where that function would experience any undefined points. There's no fractions, there's no radicals, there's no logarithms, so it should be perfectly fine as is. Now, as far as the answer for the final function, that's the domain, but we have to also consider the function that went inside to produce this final function. In other words, the function that we inserted into f of x, right? Because it was f of g. When I say inside function, I'm referring to this guy. He's the inside function, right? The one going into f in this case. So I have to look at g and I have to consider its domain as well. Well, it turns out in this particular case, g is also polynomial in nature. So the inside function is basically also from negative infinity to positive infinity. What we have to do is take the intersection of these two domains to get the final domain. And ultimately in this case, the intersection is just the same result, negative infinity to positive infinity, because the intersection of two sets that are identical is the set itself, right? So since these are the same, the intersection is the set itself. And again, don't forget intersection means what the two sets have in common, right? And of course, since they're the same, they have themselves in common. So this is our answer for the domain. All right, let's look at B now. For B, we're going to do the same kind of thing. We're going to do f of g. So we're going to take the f function, write it down, but leave a space wherever there was an x previously. So we'll have 2 space, right, fraction bar, space, plus 1. And in the space, we're going to put in the inside function, which in this case is g. All right, from here, it's just a matter of cleaning it up a little bit. So we'll multiply the 2 as 2 over 1 times 1 over x. It'll end up giving you 2 over x, right? And that will be divided by 1 over x plus 1. You can rewrite that if you want as 1 over x plus x over x. This way they have common denominators. And then from there, you can say 2 over x over 1 plus x over x, right? Remember, when two fractions have a common denominator, you add the fractions, numerators, and keep the denominators the same. And then from here, this can just be rewritten a little bit. 2 over x divided by 1 plus x over x is the same as saying 2 over x times x over 1 plus x. And then you can cancel out the x values here and just end up with. So remember, when we rewrote that in that last step there, we're using the idea that dividing fractions is the same as multiplying by the reciprocal of the second fraction, right? So we take 2 over x times x over 1 plus x. And we end up with this final result, 2 over 1 plus x. All right, so there's our composition function, our composite function. That's our f of g of x that we've been trying to find. All right, we have that. That's great. Now from here, we have to consider the domain. So to look at the domain here, we have to think of two things. The final function, right? And that's the 2 over 1 plus x. If we look at that one, we'd say, well, there's going to be some restrictions here. We do not want 1 plus x to end up equaling 0, right? That means that x cannot equal to -1, because if x was -1, then 1 plus -1 would give you 0. So we have a restriction there, and that means that the domain at that point is going to be basically from -infinity up to -1, but don't include -1, then pick up from there at -1 and go all the way up to positive infinity. Now, that's the domain of the final function, but remember, you also have to consider the inside function. What function do we put inside? Well, since it's f of g of x, g was the inside function, and in that function, we had 1 over x. And remember, 1 over x has a restriction as well. In that function, x cannot be equal to 0, right? Because if x was equal to 0, it'd be undefined. So we're going to have to also leave out 0 from the final domain, right? So because we know that x can't be 0, we have to incorporate that into our domain. So let's add that as a restriction. So we're going to say our domain finally for this final composite function is from -infinity to -1. Then we're going to go from -1 to 0, closing off the 0 again, picking up again at 0, all right, okay, round parenthesis, so we're not including 0. And then we go from 0 to positive infinity. So we had to exclude the -1 and the 0, which is what we've done by writing our domain in this way. If you wanted to write it in words, you could simply say all real numbers except for -1 and 0.